Let's start talking about centrifugal pumps, the most commonly used pumps in chemical industry. The picture on the left is a nice picture from the Bell and Gossett catalog. You see here's this electric motor, and it drives the shaft. Here's the housing of the pump, and inside the pump, if you look inside, there's this impeller which spins because of the electric motor, and the fluid, because of the spinning, gets thrown outwards by centrifugal force. It gets energized and it gets shoved out the exit of the pump. Here's the pump inlet, which I'm indicating here. That's over here, and the fluid gets thrown outward. And here's the exit, and both of them has flanges so that you can attach a pipe to it. And this second picture is an old one from this source over here. So what are some things to say about this? The first idea is very important. The electric motor is strong enough to maintain a given rotation rate, usually revolutions per minute, of the impeller within the housing. The motor is strong enough to do that. And as we'll see in the catalog, different centrifugal pumps are designed to run at a different constant rate, so and so many RPMs. So it's not as if you're changing the speed at which the pump rotates to change the flow rate. That's not what's happening at all. The impeller just rotates at a given number of RPMs. The business about the electric motor being strong enough to maintain that flow rate no matter how much you choke off the flow with a control valve. Imagine that you're in the middle of a lake and you consider the lake to be a ridiculously large housing, and you've got a little propeller in your hand and you dip it in the water and you spin it. Clearly your fingers are strong enough to rotate that impeller in this giant housing. Of course, the fit between the housing and the impeller is much tighter in a centrifugal pump, but you can just assume that even if the control valve is completely choking off the exit, the electric motor is strong enough to keep that impeller rotating at that constant speed. Important point. Another important point. This is not a positive displacement pump. It's not like a gear pump or another kind of positive displacement pump, which guarantees a given flow rate at a given setting and will rupture a pipe if necessary downstream to keep giving that flow rate. The flow rate is actually determined by an interplay between the impeller rotating in the pump and the dynamics of the piping system, and that actually we talked about in the previous video segment. That was given by the system curve. What you're most interested in when talking about a centrifugal pump is the pump characteristic, which says how the pump operates. Important point to stress, the characteristic is a curve that applies to a given impeller. So if you have a bigger impeller in the pump, you get one characteristic. If you have an alternate smaller impeller inside the pump, you get another characteristic. So a pump characteristic applies to a given impeller. What is the pump characteristic? It's a graph. On the horizontal axis is the volumetric flow rate. On the vertical axis is the head that's provided by the pump at that flow rate. So let's look at one. Here from the Bell and Gossett catalog that's been posted, here's a pump. It's called 1.5 BC. It operates at 1150 RPMs. And here's all this information. What do we want to look at? First, let's look at the axes. You'll notice horizontal axis is flow rate. For convenience, so you don't have to do unit conversions, it's given both in gallons per minute, very common units, and also cubic meters per hour. And on the vertical axis is the total head provided by the pump. And again, to avoid having to convert units, it's given in both feet and meters. So the axes are exactly what we said and what we expected. For a given impeller, so for this particular pump, there are 5 possible impellers that you can use. For the largest one, the 9.5-inch diameter impeller, this is the characteristic. So that's the relationship between volumetric flow rate on the horizontal axis and head on the vertical axis. You could also say it's the total head provided by the pump as a function of volumetric flow rate. If you put in a smaller impeller, you get this characteristic. If you put in a yet smaller impeller, you get this characteristic. So each of these curves, which starts out pretty horizontal and then begins to take a nosedive, those are 5 characteristics for 5 different impellers. You would always use an actual pump with a particular impeller, so it's one of these curves that applies to your pump. That's the most important information. However, there's also other information here. You're doing a certain amount of work per time or power on the fluid, but how much electrical power do you have to supply? Well, the work done on the fluid, or the rate of doing work on the fluid, is divided by an efficiency. And so these curves here are curves which tell you the efficiency. So if you're operating at this particular point, or actually anywhere along this curve, you have 61% efficiency at converting electrical power into mechanical work. This is the curve for 60% efficiency. This is the curve for 58% efficiency, 55% efficiency. So just kind of by interpolating between these curves, at any particular operating point here, you can tell what is the efficiency of the pump. We're going to talk about this later, but I just want to alert you to it. Here's this net positive suction head required, NPSH required curve. This is other information about the pump, which we haven't talked about yet, and I'm not touching in this video segment, but the axes that apply to this curve are the horizontal axis, that's flow rate, but you don't look to the left, you look at this right axis, the NPSH required, and it's given in feet and meters over here. So this curve, we're not going to touch it for now, but when you use this curve, you want to look along the right axis. So that's the key information that's given about the pump. What is the total head that the pump provides as a function of the flow rate? Next question. How do you choose a pump from the catalog? Well, you have in mind a certain flow rate, so that's this vertical green line, and when you're operating at steady state, given whatever the elevation change is and the pressures are and the fittings are, maintaining that flow rate in your process requires a certain amount of work or a certain total head. That's this horizontal green line. And so at steady state conditions, you want to be operating here. You want to pump so that the characteristic kind of passes through this point and you're operating at a relatively high efficiency. So you don't want to be here where the efficiency gets low. You also don't want to be here where the efficiency gets slow. You kind of want to be in the sweet spot over here where the efficiency is relatively high. So that's the goal. Again, given what your process is, you want to be operating at a certain steady state rate, so at a certain flow rate here, and at that flow rate, there's a certain amount of head needed, and so that defines an operating point on this diagram, and you want a centrifugal pump where all the characteristics are kind of around here. What I just showed you was the characteristics for a given pump. Actually, at the very front of the catalog is this picture, and it doesn't show all the detailed characteristics, but what it does show is kind of the swath that are covered by the characteristics for the different impellers that you can order the pump with. So, for example, this kind of swath here is what I've circled in red here. And as a hypothetical example, if I kind of want to be operating at a flow rate around here, and at that flow rate, the head I need to pump the fluid through my piping system at that flow rate is here, this is kind of where I want to be operating. So actually, this is too small for me to see the name here, but it's clear that I kind of want this pump. And then I go to the page in the catalog, which tells me all about this pump, which means I want to go to the page which has the characteristics for that pump. And so then if I'm on that particular page, then you sort of do the fine tuning. So it's pretty clear here that to use this particular pump, the best impeller is the middle one, which I guess is the 8.5 inch one. That's the one which is kind of the most appropriate for this combination of flow rate and head. So what we've talked about is the characteristic of a pump, which is the total head provided by the pump as a function of the flow rate. And we've also talked about how you choose an appropriate pump. And to make that choice, you have to know kind of roughly what flow rate you want to operate at and what the head is required to maintain that flow rate in your steady state process. And then you go to the front of the catalog and find which of the pumps is in the right ballpark. And then you turn to that page of the catalog and you do the fine tuning by finding the impeller which is best suited to the combination of flow rate and head that you need. So at this point, we've talked about the two most important things. For a given piping system, what is the system curve for that piping system? We talked about that before. And now we've talked about the pump characteristics. I just can't help noticing that both the system curve and the pump characteristic involves a graph where the horizontal axis is flow rate and the vertical axis is total head. And that kind of makes you think that if we put those two pieces together, we could figure out what valve position is going to give you what flow rate in your piping system, and that's actually where we're headed in the next video segment.